Y'all such nerds, I find it quite absurd. Let's talk LimSups and LimInfs. Suppose we have a sequence of numbers, which we talked about in the previous video. Notice if I start the sequence at a given capital N, so both of these, we are starting the sequence at some capital N. Even though the sequence is defined starting at 0, we might start it later. Then alpha sub n and beta sub n respectively are the supremum and infimum of whatever sequence is defined by starting at a later term and then going on and on. So for example, suppose we have the following sequence. We have x sub n starting at 0 and going to infinity is given by the formula x sub n is 2n plus 1. So the sequence is just starting at 0. We have 1, 3, 5, 7, 9, 11, and so forth. Then we can start this at any capital N we want and going off to infinity. And what we'll end up with is 2n plus 1. That's what we would get if we plugged in capital N. Now if I plug in capital N plus 1, we're going to end up with 2n plus 3, and then 2n plus 5, and so forth and so forth. Okay. We can do something a little different. I could do something like maybe x sub n is equal to n over n plus 1. So we'll end up with 0 over 1, 1 over 2, 2 over 3, 3 over 4, 4 over 5, and so forth. Okay. And I can start this, just like we did in the previous one, we can start it at a later term, in which case I'm going to start with capital N over n plus 1, and next would be capital N plus 1 over capital N plus 2, and so forth. Okay. Now we can define alpha n and beta n to be the supremum and infimum of what is found here. Now it's not immediately obvious in this case, but alpha n, the supremum of everything that comes starting at capital N and going on and on, is actually 1, and beta n, the infimum, starting at capital N and going to infinity, is the first term n over n plus 1. But in either case, by starting the sequence at a later term and then going on, we can take the supremum and infimum of whatever remains. And in this case, notice that the supremum does not depend on capital N. I'm always going to have a supremum of 1, but the infimum actually does. If I start it at a later term, the infimum is actually changing based on what that capital N is. So the infimum of a non-empty set can't exceed the supremum, which means that the alpha n's, the sups, are bigger than or equal to the beta n's, the infs. Also, we're talking about subsets here. If I move to the next cutoff point compared to the previous one, I have removed one term of consideration, so I have a subset. And sups of subsets are less than or equal to the sups of the bigger sets. So the supremum of what comes from the term n plus 1 and beyond is less than or equal to the supremum of what came at term n and beyond. The infimums can only get larger. Okay. Altogether, if I piece these inequalities in one big line, we get the following. The infimums only get larger, the supremums only get smaller, but the supremums are always bigger than or equal to the infimums. So we get this infinite chain of inequalities. And remember, beta sub n is the infimum of all the terms from n and beyond. Alpha sub n is the supremum of all the terms from n and beyond. So if I cut off the first term, or the first two, or the first three, we're just moving from subsets to subsets to subsets. Infs are getting bigger, sups are getting smaller. Those are the outer inequalities, but at the middle we see that infs are always less than or equal to sups. So this increasing chain of infima cannot ever surpass the decreasing chain of suprema. So we start with the sequence, yes. And we have now made two new sequences. That is correct. So whatever the sequence xn was, now we have two associated sequences, a sequence of suprema and infima of different cut-off versions of the original sequence. Okay, so we've got this sequence of suprema, the alpha n, and the sequence of infima, the beta n. So we define the following. Alpha is the infimum of all the alpha n's. So it's the infimum of all of the supremas of the various cutoff versions, and we call that the LimSup, the infimum of all the supremums, and conversely, beta is the supremum of all the infimums, and it's called the LimInf of the original sequence. And the notation is given on the right there, LimSup as n goes to infinity of xn. That is the infimum of all the suprema. LimInf as n goes to infinity is the supremum of all the infima. So the inf of the sups is the LimSup, and the LimInf is the sup of the infs. It's a little confusing at first, but trust me, you'll get the hang of it. So here is our first theorem about these convoluted disasters. If xn is a sequence, and I have a LimSup, remember that is the infimum of the sequence of the suprema, which is alpha, and the LimInf, that's the supremum of the sequence of the infimums, call that beta. Beta is less than or equal to alpha. And yeah, infs in general are smaller than sups, so we would expect beta to be less than or equal to alpha. But remember that beta is the supremum of an infimum sequence, and alpha is the infimum of a bunch of suprema. So how does that make those two things play off on each other? We have to figure it out. Okay, so if we define alpha n and beta n as we have before, and we have this chain of inequalities, assume to the contrary that beta is actually bigger than alpha, which means I can find some real number x in between beta and alpha. So we have beta 1 less than or equal to beta 2, less than or equal to beta 3, and so forth. And similarly, alpha 1 bigger than or equal to alpha 2, bigger than or equal to, and so forth. But somehow, this is going to end up at beta, and this is going to end up with an infimum of alpha, and I'm just picking some x that is in between. Okay, so here's where our assume to the contrary that beta is bigger than alpha, and we pick an x in between. Now, since x is less than beta, it's less than the supremum, but the supremum is an upper bound, and it's the smallest upper bound. So since x is smaller than the supremum of the betas, x is not an upper bound of the betas, which means there has to be an element of that sequence bigger than x. Remember, the betas are a sequence of infima. And if x is less than its supremum, then something in that sequence is bigger than x. Conversely, something in the sequence of the alpha n, the supremums, since x is bigger than that infimum, then x is not a lower bound, so something in the sequence of alphas must be less than that x. So pick whichever one of those two indices, the beta that we picked that's bigger than x, or the alpha that we picked that's smaller than x. Pick whichever index is bigger, and then look what we get. Okay, so m is bigger than n1, and the betas were an increasing sequence. So since m is at least as large as n1, beta m is bigger than or equal to beta n1, but beta n1 was bigger than x, because x was smaller than the supremum of the betas, so I picked that particular beta to be bigger than x, because x was not a upper bound of the betas. However, for any particular index, the infs are never bigger than the sups. But since the sups form a decreasing sequence and m is at least as large as n2, the larger index, which is m, makes a smaller supremum. So alpha m is less than or equal to alpha n2. But again, x was chosen to be bigger than alpha. Alpha was the infimum of the suprema. So x is not a lower bound on the suprema, and alpha n2 was the supremum that was smaller than x. And overall, if I look at the exterior sides of this inequality, what do we have? X is less than x, and that's flatly a contradiction. Okay? So this increasing sequence of infima cannot somehow cross places with the decreasing sequence of suprema. So whatever the supremum of the infima, okay, the sup of the infs, that's the LimInf, that's what we called beta, it's never going to be larger than the inf of the sups, or the LimSup, alpha. Basically, to redraw the picture we had before, here are our beta n's, they're increasing. Here are alpha n's, they're decreasing. If somehow beta, which was the LimSup, sorry, the LimInf, okay, the supremum of the betas, if somehow that was bigger than alpha, the LimSup, okay, the LimSup is the infimum of the alpha ends, and beta was the supremum of the beta ends. If somehow they crossed places, then these alpha ends would have had to decrease their way down here, but these beta ends would have had to increase their way up here, and you'd end up with a problem where the betas somehow got larger than the alphas. So in general, infs are smaller than sups, and that has been preserved. The LimInf of a sequence cannot be bigger than the LimSup of a sequence. Yeah, they might be equal. So some exercises working with these concepts, okay? The first one is really the most important, and we've already done half of it, okay? But specifically, LimInf and LimSup always exist. And then some other results here dealing with some specific sequences. So pause and get to it. So hopefully we had some luck. Let's move on to a useful result that we'll actually prove together. So suppose xn is a sequence, it has LimSup alpha, and beta, here beta is not necessarily the LimInf, it's just any number. Beta is smaller than alpha, and k is any natural number. Then there must exist some natural number at least as large as k, so that that index x sub n is bigger than beta. If you pick anything smaller than the LimSup, you can always find terms of the sequence bigger than that. In other words, you can do that infinitely many times, okay? If you can always find terms of the sequence bigger than beta, larger than k, where k is anything you want, then you can find infinitely many. So here's what we're going to show. So I've got the sequence xn. Here's alpha. This is the LimSup of the xn. And I pick any beta I want. It's just got to be less than alpha. Now you pick an arbitrary natural number, and what we do is we find an n that's at least that large, and x sub n is bigger than beta. So I can find one particular x sub n bigger than beta, but if I then take this n and I just replace k with that n plus 1, then I can find a new natural number at least as large as m plus 1, so that xm is bigger than beta. So I can find another one in here. And then if I just replace that index again and I find a new term, again. So if you can do it once, you can do it infinitely many times. Anything less than the LimSup of the sequence, there will be infinitely many terms of the sequence bigger than it. So let LimSup be alpha and k be arbitrary. These were part of the theorem. So by definition, alpha is the infimum of the suprema. So beta is less than alpha. Alpha was the infimum of all of the alpha ends, which means it's a lower bound on the alpha ends. And since beta is smaller than that, beta is also a lower bound on the alpha ends, but it was strictly smaller than alpha. And therefore, beta is strictly smaller than every single alpha n. And that's what we have right here. Beta is strictly smaller than every single alpha n. Okay. Specifically, beta is smaller than alpha k. So since beta is strictly smaller than alpha k, which is the supremum of a set, it's not an upper bound on that set, which means something in that set must be bigger than beta. But this set was the terms of the sequence beginning at index k, so there must be an index at least as large as k, so that x sub n is bigger than beta. Okay, some similar results. What we showed on the previous slide is anything smaller than the LimSup, there are infinitely many that are bigger than that. That's number one, and we already proved that. But there are variations on this. Anything bigger than the LimInf, there are infinitely many which are smaller than it. Anything bigger than the LimSup, there are only finitely many bigger than it. And anything smaller than the LimInf, there are only finitely many lesser than it. So get to work. Number 2 is very similar to number 1, and numbers 3 and 4 are very similar, but you've got to do each of them individually. So hopefully you were able to piece that together using very similar arguments to the previous theorem. Now here is one definition that's really going to tie a bunch of stuff together. So for any sequence, here's what we have all put together. The LimInf of the sequence always exists. The LimSup always exists. The LimSup is never smaller than the LimInf. So here is one definition that ties together pretty much the rest of calculus for this course. If the LimInf and the LimSup are the same number, notice the LimInf has to be less than or equal to. If they happen to be equal to each other, then we say the limit of the sequence exists and is given by this shared value, which might be plus or minus infinity, or it might be a real number. But if it's the same thing, that's what we call the limit of a sequence. So if I have my beta n's increasing towards beta, this was the LimInf, and I have my alpha n's, these are decreasing to the same thing, this was the LimSup of the original sequence xn. If alpha is equal to beta, then we call that the limit of the original sequence. Now you may have come across definitions of limits before where the limit definition is done differently. Yeah, there's an epsilon, and LimSup and LimInf, if they were addressed at all, they don't come until later in the course after you've already talked about limits. We're just doing things a little differently this time, but that's okay. Here's one of the most important results in real analysis, and it's a nice thing to come early on. Suppose that xn is a monotone sequence, then the limit exists. Possibly plus or minus infinity, but either way it exists. So the sequence is assumed to be monotone, which means either monotone increasing or monotone decreasing. We're just going to assume it's monotone increasing, and the very similar proof for the case of monotone decreasing you guys can put together yourselves. So since the LimInf and the LimSup already exist, they always do, and the LimInf is always less than or equal to the LimSup, we only need to show that they're equal, so let's assume to the contrary that they're not. But since the LimInf is less than or equal to, if it's not equal to, then the LimInf is actually smaller than the LimSup. So now what we're assuming is I have xn is monotone increasing, and remember alpha n, this is the supremum of the terms starting at n and going to infinity. Beta n, that's the infimum of the same thing. And what we've just assumed is that beta, which is the supremum of all the beta n's, is actually smaller than the infimum of the alpha n's, which was alpha. Okay, so the xn is monotone increasing. So here are my xn's, they're monotone increasing. My supremums are decreasing, my infimums are increasing, and we're assuming that they don't quite join together. So pick some real number y that is in between the LimInf and the LimSup. This can be done even in the case of some infinities in there. Okay? If the LimSup is infinite or the LimInf is minus infinity, you can still find real numbers in between. So since y is less than the LimSup, from previous slides, there are infinitely many xn bigger than that. So pick one of them. Okay, there are infinitely many. Let n sub 1 be an index so that that particular x is bigger than y. We've already shown that any number less than the LimSup, there are infinitely many terms bigger than that y, so just pick one of them. Since y is bigger than the LimInf, there are infinitely many xn's smaller than it. So pick one of them, and specifically I want to make sure that the index n2 that I pick here is bigger than the index that I picked before. Since there are infinitely many xn smaller than y, I can always find one of arbitrarily large index, which means I can find an index bigger than n1. If I couldn't find an index bigger than n1 that would do this, then my only options would be 1 through n1, and that's finitely many indices. Since there are infinitely many xn's less than y, I can find an index so that xn2 is less than y, and that index was bigger than the one I already picked. But now I have xn2 is less than y, but y is less than xn1, but n2 is the larger index. So I have a larger index term smaller than a smaller index term. But this was a monotone increasing sequence. As the index gets larger, the terms can't get smaller. So here's our contradiction. So the contradiction was generated by the assumption that the LimInf was smaller than the LimSup. So if the LimInf can't be smaller than the LimSup and it must be less than or equal to, the only other option is that they are equal, and therefore by definition the limit exists. So monotone sequences always have limits. If the sequence is bounded, then the supremum and the infimums are always real numbers, and it follows that this limit must be a real number. So altogether, a bounded monotone sequence always has a limit which is a real number. And this is a really important thing, and we'll use it several times throughout the course. A bounded monotone sequence has a limit which is a real number. Yes, bounded monotone sequences have real limits. Great. So do a couple further exercises. Suppose you have a monotone increasing sequence. Prove what we just explained, that if the sequence is bounded, the limit doesn't just exist, but it's not plus or minus infinity. Conversely, if it's unbounded, then the limit is plus infinity for a monotone increasing. All right, let's move on. Here's the traditional definition that you may have seen before. Suppose I have a sequence xn and I have a real number a. Then the definition we had before about LimSup equaling LimInf being the number a, that happens if and only if, for every epsilon which is positive, there is a capital N which is a natural number, such that for any n bigger than or equal to capital N, the distance from xn to a is less than epsilon. There's your traditional definition of a limit that you may have seen in calculus textbooks before. Yep. The number epsilon on the right here represents some sort of allowable error. Our goal is to force a distance from xn, a term of our sequence, to a, the goal, the limit, and that distance needs to be less than epsilon. So the terms of the sequence have to be within distance epsilon of a, and epsilon is for any positive number, so imagine it to be very small. Okay. So we need terms of the sequence to be very, very close to a. What does capital N represent? Well, once you've started off by saying epsilon's a positive number and it's very small, I want my terms of the sequence to be that close to a. Capital N must exist. It's some cutoff point so that every term past that point is very close. Pick your allowable error, which is allowed, and it must be positive. You can't set epsilon to equal 0. There exists a cutoff point so that every term past the cutoff is very close to a. How close? Epsilon close. So no matter how close you want the sequence to be to a, there is a cutoff point so that past that point, every term is that close. No matter how close we demand the sequence be to a, eventually, in other words, past capital N, the sequence remains that close to a. It is not enough to occasionally be close to a. No matter how close you want to get, there must be a cutoff point, capital N, past which every term, for any n past n, every single one of those is very close to a. So you get close to a and you are trapped close to a. So here's our number line. Here's a. The sequence is bouncing all around and doing who knows what. Pick epsilon, which is positive. The goal is to get xn minus a to be less than epsilon, which is exactly the same as saying xn has to be in between a plus epsilon and a minus epsilon. So what you end up doing is you define a sort of allowable zone from a minus epsilon to a plus epsilon. And I've defined a little interval here. And what has to happen is there must be a cutoff point, capital N, so that for anything past that point, we get this. So x sub 1 might be way off here, and x sub 2 might be way off here. Maybe x sub 3 is in the desired range, but x sub 4 isn't. Maybe x sub 5 pops back to be very close to a, and so is x sub 6, but then x sub 7 is way off here. But eventually, there will be a capital N so that x sub n is in here, x sub capital N plus 1 is in here, x sub capital N plus 2 is in here. All the remaining terms are trapped. And then you can do this over and over again. You can come back here and pick a new epsilon, make it smaller. There will be another capital N, probably a larger one, so that past that point, everything is this close to A. Then pick a smaller epsilon. Past a certain point, everything is this close to A. Pick a smaller epsilon. Past a certain point, everything is this close to A, etc., etc. This is your epsilon definition of a limit. For any epsilon which is positive, it defines this little interval around A. There will be a cutoff point past which every term of the sequence is trapped there. So here's a theorem. Okay, we want to show that our definition from earlier about LimSups and LimInfs is really the same thing. So naturally, there's going to be two steps. First, we're going to assume our version, the LimInf and the LimSup are the same. Then we need to show that this other epsilon thing happens. So we get to assume this. Now we need to prove that for any positive epsilon, there is a capital N, etc., etc. So since we need to prove something about every positive epsilon, just pick positive epsilon and let it be arbitrary. But now A minus epsilon is a smaller number than A, and A was the LimInf. But A plus epsilon is a bigger number than A, and A was also the LimSup. So from earlier exercises, we know that since A minus epsilon is less than the LimInf, there are only finitely many terms less than A minus epsilon, which means past a certain point, they are all bigger than that. And since A plus epsilon is bigger than the LimSup, there are only finitely many terms bigger than that. In other words, past a certain point, they're all smaller than that. So there must be two different cutoff points, N1 and N2, so that past N1, we are always bigger than A minus epsilon, and past N2, we are always lesser than A plus epsilon. If I represent what's going on here, A plus epsilon is bigger than the LimSup of the xn, which means only finitely many terms can be bigger than this. But A minus epsilon is smaller than the LimInf, which means only finitely many can be smaller than that. If there's only finitely many terms bigger than or equal to A plus epsilon, there was a last time it happened. And if there are only finitely many terms less than or equal to A minus epsilon, there's a last time that happened. If I go past both of those times, I'm trapped. Okay, so if I go past the maximum of those two indices, capital N1 and capital N2, if I go beyond that point, I get both inequalities we needed. I am less than A plus epsilon, but also bigger than A minus epsilon. In other words, the distance to A is less than epsilon, and that was what we needed. So if we assume our version, that the LimInf and the LimSup are the same, we can derive the same thing in the epsilon definition. We have to go the other way, though. Assume that the epsilon definition holds. For any epsilon, there is some capital N, so that for any little n past that point, we have x sub n is in the interval from A minus epsilon to A plus epsilon. The distance from xn to A is less than epsilon. We now need to show that the LimInf and the LimSup must both be A. Okay, but what we have assumed is no matter what epsilon you pick, eventually everything is trapped here. There must now exist an n so that if n is bigger than or equal to that, all of the xn's are trapped. So now think, if all of the xn's after capital N are in here, how many of them were not? How many of them were bigger than A plus epsilon or less than A minus epsilon? All of them past capital N are in the little interval, so only finitely many of them are not. Okay. So therefore, since all of the xn's past a certain point are within the interval A minus epsilon to A plus epsilon, once I take n beyond that cutoff point, they're all between A minus epsilon and A plus epsilon, which means the infimum can't be less than A minus epsilon. If they were all in between A minus epsilon and A plus epsilon, their infimum cannot be any smaller than that, because A minus epsilon is a lower bound. All the terms were bigger than or equal to A minus epsilon, so A minus epsilon is a lower bound, and the infimum can't be smaller than any particular lower bound, because the infimum is the biggest of all possible lower bounds. Similarly, if all terms of the sequence past capital N are trapped in this interval, the supremum cannot be any bigger than a plus epsilon, which means past capital N, my beta n's are bigger than or equal to a minus epsilon. Okay, so the supremum of them is also bigger than or equal to a minus epsilon. If some of them are bigger than or equal to a minus epsilon, certainly the supremum of them is bigger than or equal to a minus epsilon. And here, some of our alpha n's are less than or equal to a plus epsilon, which means the infimum of them is also less than or equal to a plus epsilon. And now what do we have? Whatever the LimInf in the LimSup are, they are in between a minus epsilon and a plus epsilon, but epsilon was completely arbitrary. So the LimInf and the LimSup can't be anything other than a. This is something we established way back, okay? If you are within epsilon distance of a for every epsilon, you are a. There is no number that is as close as you want to a without actually being a itself. And since the LimInf and the LimSup were both trapped within epsilon distance of a and epsilon was arbitrary, they are both equal to a, and we recover our version that the LimInf and the LimSup are the same number. They are equivalent definitions. So why have we introduced them in what is considered a non-standard order? It really is pretty unusual to define LimSup and LimInf before talking about limits. Usually you get this epsilon definition of limits and then you define LimInf and LimSup. Well, yeah, it doesn't really matter. Once you establish they're the same definition, that one implies the other, the order in which you do it is kind of irrelevant. Now, me personally, I kind of like something about the LimInf-LimSup approach. The epsilon definition of a limit requires you to have this letter A that you're comparing terms of the sequence to, and our definition of LimSup-LimInf didn't require that extra knowledge. Okay. So a couple of just small remaining problems at the end. Suppose xn is a sequence, a is a real number. This is just a way to relate our version of LimSup and LimInf when the limits are infinite or minus infinite to a sort of not really epsilon version, but the more traditional way of defining those limits. They are equivalent based on our definition, so work through those equivalences here. Okay, so what we're showing is, if I want the limit of xn, for example, to be infinite, then on the one hand, we have LimInf xn equals plus infinity equals LimSup xn. And I want that to be if and only if, given any cutoff point, capital T, which is a real number, so I'll just throw it down here on the real number line, there exists a cutoff point index so that given any little n past that point, xn is at least as large as t. So x capital N plus 1, doesn't have to be a monotone sequence, so maybe I go back on myself a little. But everything past this point is bigger than t. And that has to be true for every t, so now you imagine moving this cutoff t forward and forward. So everything is bigger than this. Past a certain point, they're all bigger than this. Past a certain point, they're all bigger than this. Past a certain point, they're all bigger than this, and so on and so on.